Thanks very much for the introduction. I'm very pleased to actually have an audience this size on the very last of, or at the end of the semester. Right, when I was preparing this talk, I was also reading this book about the Fukushima nuclear disaster. I recommend it. It's a riveting story of what happened at Fukushima. And it also speaks to the issue of the regulatory environment in Japan and in the United States and why such nuclear accidents happen. And so while I was reading it, or when I finished reading it, I really had to ask myself, why do I keep talking about nuclear topics? I mean, this was a horrible event, a very discouraging event, and one that certainly encourages a person to look at other or alternative energy sources. But at the same time I was reading about Fukushima, the assessments by the Intergovernmental Panel on Climate Change, the fifth assessment was coming out, which very clearly demonstrated that climate change is upon us and that the effects are many, and that the effects are happening more rapidly than anticipated. And of course, this drives one to think of alternatives to fossil fuels. And back to nuclear, the attraction is that there's just so much energy per unit mass available if one considers nuclear power. Another way to say it is that there's not much energy associated with the electronic transitions that take place by combustion of fossil fuels. At most, you liberate a few parts of an electron volt, maybe a few electron volts, as compared to the energy available to tapping the forces that hold the nucleus together. And there we get a millionfold more energy out of the nucleus than we do out of these electronic transitions. Another way to say it is if you burn a mole of methane, you only get maybe 800 kilojoules, which isn't actually very much energy, and a mole is 10 to the 23rd atoms. Okay, so you have to divide, if you want to know how much you're getting per event, if you do the math, you'll see that, again, it's just a few electron volts. I'll show you in a moment that with fission, you get a lot more energy. So what I want to do is pursue this theme of nuclear power, the nuclear fuel cycle, and the carbon cycle. I've reduced it to what I think is the critical question, that is the question of plutonium generated in the nuclear fuel cycle versus carbon, mainly in the form of greenhouse gases emitted to the atmosphere. I want to acknowledge Energy Frontier Research Center that I participate in, where the subject is the material science of actinides, and you'll see some of that work today. I also just have to say that although I'm a member of the Nuclear Waste Technical Review Board, this presentation represents only my own views and certainly is not an opinion or the views of the board. What I'll do is I want to speak very broadly, do a lot of arm waving, because I think the context of the problem is really everything in terms of deciding what science and engineering needs to be pursued. Then I want to give you very quickly some samples of the science that my research group has done to address some of these issues. The science is actually a little bit old. The research group has moved on to other exciting topics, but I want to present to you some ideas that come from what we've done in the science and engineering, mainly material science. And then finally, I want to discuss the situation in the United States, a very specific example. The situation is a description of how we handle the plutonium from dismantled nuclear weapons, because that's a good example of our success or failure in addressing the plutonium part of this presentation. All right, to give this the widest context, if we look globally, the first thing we have to ask ourselves is, what is the carbon cycle? And I'll represent the different parts as gears in a machine that drives the Earth. And the carbon cycle, this is a simple representation, but it's meant just to emphasize that if we keep track of the movement of carbon through or around the Earth, it's complicated. There are a lot of parts to the carbon cycle that we are still studying and trying to understand. And the connection of the carbon cycle, this complex geochemical cycle, to the nuclear fuel cycle comes when we substitute nuclear power plants for, say, a coal-burning power plant. Okay? That's where we look for the connection. And so then we have to look at the relation of nuclear fuel cycles to the carbon cycle. And already an immediate question should be, well, how big does this nuclear fuel cycle need to be to have an impact on the carbon cycle? And then also, it's important to realize that there are many different nuclear fuel cycles, so the answer won't be necessarily very straightforward. We can start by looking at the process of fission, and this is my 101 version of fission, but it captures the important parts or aspects that I'll be discussing in terms of fuel cycles. First, there are two isotopes of uranium, uranium-235 and uranium-238. 235 is not very abundant. Less than 1% of the uranium atoms you pull out of the ground will be uranium-235. But it's the isotope uranium-235 that we fission using slow neutrons, thermal neutrons, that travel at about 2 kilometers per second. These thermal neutrons can split uranium-235 because its concentration in natural uranium is so low. In most nuclear fuels, we enrich it to, say, 3 to 5 atomic percent so that we have enough uranium-235 to fission in the reactor. We have a slow thermal neutron. It splits the atom and gives us this bimodal distribution of fission fragments, which give us elements that have atomic numbers or atomic masses that are about half of that of the uranium-235 nucleus. So this bimodal distribution has two peaks where we have atoms like, well, cesium-137, technetium-99. These are the fission fragments that result from the fission event. These, I've put them in orange, are actually the main waste products. Okay, one can imagine using some of these highly radioactive fission fragment elements for one application or another, but in fact that hasn't panned out very well. So the fission fragment elements captured in this bimodal distribution, these are the things that we have to dispose of. We have extra neutrons that are traveling at very high velocity, say 20,000 kilometers per second. They have to be slowed down, and so in a reactor we have a moderator, say carbon, that slows them down by collisions, and then these slow-moving neutrons can continue in a chain reaction to fission the uranium-235, and that fission event, by the conversion of a little bit of mass to energy, releases per event 200 million electron volts. Okay, so it's huge for each fission event as compared to the combustion of carbon fuels. Okay, so this is what most people are familiar with in terms of fission reactions. But a very important reaction that also occurs is the uranium-238, which isn't fissioned. It's a pity because it's so abundant, making up over 99% of the uranium that we pull out of the ground, it captures these slow-moving neutrons, and then by a series of decay events, we generate plutonium-239 and minor actinides. I'll come back to that in a moment. But the plutonium-239 can be fissioned by the thermal neutrons. And so the plutonium-239 in the reactor fuel is fissioning, gives slightly different array of fission fragment elements. But it grows into the fuel over time. And in fact, in a typical light water reactor, about a third of the energy comes from fissioning the plutonium-239. By decay and various nuclear reactions, we also generate neptunium, americium, and curium. These are the minor actinides. And generally, we would consider these as waste products. Although something like neptunium, we can certainly fission or make a nuclear weapon with that material. So the important element from my perspective is the plutonium that grows into the fuel. Okay? The plutonium is great if you're a nuclear engineer, because then we want to put that back in the reactor in various types of fuel and fission it and extract the energy. It's great if you're making nuclear weapons. You can use that plutonium-239. It's not so great if you're worried about the environmental impact of the release of plutonium, because this has a high radiotoxicity. And in fact, as one looks at this very simple picture, I'd argue that, and I'll show you different fuel cycles, all the different fuel cycles, the different strategies, they just represent an effort to handle the fissile material, which is the uranium-235 that's left over, and the new plutonium-239 that's grown into the reactions. And if we look at a simple representation of the fuel cycle going all the way from mining to enriching the uranium-235, fabricating a fuel, putting it in a power plant, generating electricity, reprocessing perhaps to reclaim the plutonium and the remaining uranium-235, this recycling or not represents an effort to handle the fissile material, to get as much energy out of it as possible, to make as many weapons as you want as possible, and even perhaps to make the nuclear waste disposal problem a little easier. Now, I picked this example, the fuel cycle, because of what it leaves out. There's no geologic repository. And this representation of the fuel cycle, I think, reflects part of the problem in dealing with nuclear waste. That is, the nuclear community designing fuel cycles until very recently haven't thought very much about the type of or the properties of a geologic repository that would be required to handle the high-level waste, which are these fission fragment elements, or the spent fuel if it's disposed of directly. So there should be a repository there. And so if there's a repository, then we have to be concerned with the geochemical cycles for the different radionuclides, right? Okay. Because we've disposed of those fission fragment elements, the minor actinides. When we put them in the ground, then the question is, will they stay where we left them? And so the boundary between the fuel cycle in the most general sense and the natural environment is the repository itself. And this is just a cartoon, but there's a lot of information here. As an example, in terms of fuel cycles, we think on the time scale of decades. In terms of repositories, release, transport, and either dilution or concentration of specific radionuclides, there we're thinking on the scale of hundreds of thousands of years. So one of the most interesting aspects of this subject is that we have short time scale events, building a nuclear power plant, building a repository, and very long-term geologic time scale events, that is the behavior of these radionuclides as they exist in the Earth. This also means, or what should come to mind is that Actually, we have two dials. If we're worried about environmental impact, the reactor side, I'll show you, there are different fuel cycles, so we can maybe make the problem worse or better by being clever about our fuel cycle, but also by being clever about our strategy for selecting a repository site and combining a site with engineered barriers. We also can control the release and the environmental impact of the system. So the fuel cycles, this is very elementary, but I think useful to realize. We have in the US an open fuel cycle. We mine the uranium, we enrich it, we fabricate a fuel, it goes into the reactor. We store it, at least the initial thoughts were we store it for not too long, and then finally it goes to a geologic repository. Okay, the fuel is not handled. In this picture, as I've just said, the parameters we have are the type of fuel, the reactor, the burn-up. All of those things affect the waste products, the array of fission fragment elements that we get, the amount of plutonium in the fuel, the amount of the minor actinides. So we can do a little bit here, but also geologic disposal isn't just a blank box, as this diagram indicates. We have a lot of choices. We could pick a granite, we could pick clays, we could pick salt, we could pick a volcanic tuff, all with different geochemical and hydrologic properties. The closed fuel cycle is one in which we add chemical processing, in which once the fuel comes out of the reactor, it's dissolved and we can reclaim a variety of radionuclides. Mainly, we're interested in reclaiming the uranium and then the plutonium-239. The plutonium can be mixed with uranium into a fuel, a mixed oxide fuel, which I'll discuss a little bit more in a moment. It goes back into the reactor, and so you close the fuel cycle into this loop, but you can't go around the loop an infinite number of times because there are other things, mainly minor actinides, building up in the loop that prevent you from very effectively using the material as a fuel. But you can make this maybe twice, maybe three times. And then in your geologic repository, you have the high-level waste, and then also the spent fuel, where the high-level waste is, again, the material left over after you have dissolved the fuel, removed the uranium and plutonium. So these are all of these fission fragment elements. Now, of course, there are a lot of possibilities for fuel cycles. So there are hybrid or symbiotic fuel cycles where you could use a light water reactor, which is taking advantage of these thermal neutrons, the slow neutrons, to fission uranium-235. But if you separated out the plutonium and the other transuranium elements, these minor actinides, you could fabricate a fuel and burn it very efficiently in a reactor which uses a fast neutron spectrum. So one of the dials you have is the energy of the neutrons, right? And so you can have different combinations of reactors that give you a waste stream. Finally, you're always stuck with the fission product elements, but this is a way of consuming the plutonium, the minor actinides, and making your problem either more complicated or less complicated. Okay? And nuclear engineers can dream up literally hundreds of different fuel cycle combinations. Okay? So the beauty of nuclear power is this flexibility in terms of being able to consume or breed an element like plutonium, to selectively fission certain elements by changing the energy of the neutrons. Okay, so this is, we've covered the geochemical cycles, which is really the waste management side. And then finally, depending on the fuel cycle you have, there's the issue of nuclear weapons and the proliferation of nuclear weapons. And one can imagine that the open fuel cycle, where the plutonium is left in the spent fuel, which is highly radioactive, might be preferable to a country pursuing reprocessing and separating the plutonium which then might be diverted to weapons. Okay? So there are lots of possibilities on the weapons side. The weapons problem, in the simplest way to think about it, comes from the fact that if you put uranium-238, the most abundant isotope, into a field of neutrons, you generate a whole series of plutonium isotopes. There are isotopes to the left and right here. I think there are 19 isotopes of plutonium. About 60% will be plutonium-239. A lesser amount will be plutonium-240. And what's very important to realize is that if you just chemically separate the plutonium, this is weapons usable. Okay? It doesn't require additional enrichment. My nuclear engineering friends would say, well, who would do that? I mean, that's such a messy material to work with. But if it's all you've got, then it's important to realize that it's weapons usable. Well, what about the plutonium inventories? Because plutonium, except in very small amounts, doesn't occur naturally. It's a man-made element. And so if we look at the inventories, from this inventory is generated by nuclear power, it's 2,300 metric tons. Okay? Keeping in mind that in terms of a weapon, we're talking about kilogram quantities. So this is a lot of potential nuclear weapons. We have about 250 metric tons of separated plutonium in our military or weapons inventories. And in a way, this is good because in general, countries keep track of their weapons, right? So this is very secure. What's surprising is that an equal amount of plutonium has been separated on the civilian side from power generating reactors. Okay? So we have as much plutonium separated from nuclear power plants, fuel from civilian nuclear power plants, as we have in weapons. And this is cared for to varying degrees of satisfaction. Okay? Also, what it represents is that actually the fuel cycle is out of balance. Remember, I have these nice boxes showing you that you separate the plutonium, you put it into a mixed oxide fuel, you run it through the reactor, you extract more energy. Those box diagrams are very deceptive because they presume that everything works the way you designed them to work. But what we can observe is globally, we've stranded 250 metric tons of plutonium in the system. Okay? And this is an important issue, and that's why I say carbon versus plutonium. Plutonium is the most interesting and I think the most problematic of the elements associated with the nuclear fuel cycle. So back to the picture of the Earth, what we can say is, on one hand, we have the plutonium, and this is the global inventory that's increasing, this horizontal red line, our area I'll talk about in a moment. But you can see that it's increasing, and it's a clear and present danger to national and international security. So we have plutonium as a problem, and then we have carbon, or CO2, or greenhouse gases in the atmosphere, as another clear and present danger, and this is just a quote from the fifth assessment report. So in a simple-minded sort of way, the question is, which problem do you want to have? Okay? Do you want global warming and to deal with that, or do you want weapons, plutonium, environmental impact, and so on? And the answer is not clear-cut. Okay? I mean, a release of plutonium might be a localized release. The detonation of a single nuclear weapon, as tragic and as horrible as that might be, it's still not global warming. So we have to make a choice between, or we don't have to, but let me suggest that we think about what the choice might be if we're choosing between plutonium versus carbon. Well, what is the connection? Okay, if I imagine, well, I'm willing to put up with a certain amount of plutonium in order to take advantage of this high energy density that I find by this process of fission. Globally, if we consider, this is in 2000, actually now I think there are 237 nuclear power plants, and we generate a little less than 17% of the world's electricity. It's more like 12 or 13% now. But taking this figure for the year 2000, the carbon reduction, and it depends on whether the nuclear power plant replaces coal or natural gas, it's on the order of half a gigaton. Now, what I forgot to say when we looked at the carbon cycle, that simple diagram was for the year 2002, when the carbon emitted to the atmosphere was about 6 gigatons. Okay? So while I've been talking about this subject for the last decade, that number's gone up to 8 gigatons. So in terms of present nuclear power production, it's only about a half a gigaton out of the 8 gigatons that are emitted. That's the scale. And in fact, we can look at lots of studies about how large the nuclear fuel cycle or the nuclear effort has to be in order to impact global warming or to impact the carbon cycle. And depending on the study, it's a factor, the proposed factors range from 2 to 10, okay? 2 to 10. And I'll just use one paper as an example of how the calculation goes. And this is a paper I like because first, it's only 2 pages, okay? Second, the authors are very distinguished in their, they've written many papers, so these 2 papers, or 2 pages, really distill a lot of very thoughtful analysis by the authors. And what they've said is, let's let the world's population level off at about 9 billion. I checked today, we're at about 7.2 billion. It won't be, I think 2024 will hit 8 billion. Let's allow the per capita energy consumption to rise by about 50%. And the energy needs then would be 900 exajoules, or if you're more comfortable with quads, it's still about 900 quads. And if we just, as a thought experiment, take those 900 exajoules per year and divide them into thirds and say, well, 1/3 will be generated by fossil fuel. That's about what we're doing now. So that means that by the year, and this is to the year 2050, that we've made great progress. We've just stayed where we are in terms of CO2 emissions. 1/3 to fossil fuels. We take 1/3 and we let alternatives, wind, solar, and decarbonized fossil fuels, that is, take credit for carbon sequestration. That group has to provide 300 exajoules or quads, which is huge. That really requires a lot of effort for the alternatives. And then the remaining 300 exajoules, we say, well, the nuclear side will take care of that. We know how to do that. Well, if we do that, it turns out we would need 3,300 gigawatt years of output annually, okay? Which is equal to about 3,300 large nuclear power plants. We have to build them by the year 2050. Do the math that we need one every couple of weeks. We will generate each year from these 3,300 power plants about 70,000 metric tons of spent fuel. So we need the equivalent of a Yucca Mountain repository every year. And I'll simply observe the country has worked on Yucca Mountain for 2 or 3 decades. And in terms of my favorite element, plutonium, we generate 70 metric tons per year. Remember, the global inventory was 2,300. So this is a huge increase in the inventory of plutonium that we propose. Now, focusing on the plutonium, there are 2 strategies, 2 categories of strategies. One is the nuclear strategy, because I've shown you these fuel cycles. We can get the plutonium back into reactors. We can consume or extract energy from them. We can do the same with the minor actinides. We use a mixed oxide fuel, a mixture of plutonium and uranium, or an inert matrix fuel. This just means a material that doesn't have any uranium, because remember, when we put the mixed oxide fuel in the reactor to burn the plutonium, we create plutonium. So the mixed oxide fuel solution leaves you with about the same amount of plutonium that you started with. Okay? That's an important observation, but different isotopic composition. And then there are another category of possible solutions. These are geologic solutions. This would be the direct disposal of the spent fuel, or if we have reprocessing, gathering the plutonium up and the minor actinides and putting them into very durable solids. So I just want to talk about the geologic aspects, and I have to cover this very quickly. The fundamental question for geologists would be, well, if I have these actinides and I put them in the ground, what do I have to worry about? What do I have to think about? And let me give you just a few of these thoughts. First, if we look at the activity of a spent fuel assembly, that's this red line. That's the total activity. So we see it takes about 1 million years, or many hundreds of thousands of years, to cross the horizontal line, which is the level of radioactivity of the uranium ore that was used to create this spent fuel assembly. Okay? So in a crude way, that's how long it takes to get back to where you started in terms of radioactivity. If we break this apart and ask ourselves how much of this activity is due to actinides versus the fission product elements, we see that the fission product elements have, relatively speaking, shorter half-lives, so they drop rather quickly. And it's the actinides that hold up the curve over these longer periods of time. So one thing we learn in terms of putting actinides, like plutonium, in the ground is that, boy, that makes my waste management problem a little longer term. Okay? It's not entirely fair because there are long-lived fission products such as technetium-99, half-life of 200,000 years, iodine-129, a half-life of 16 million years, and so on. But it's mainly the actinides that hold the curve up. Also, if we look at the composition of the fuel over time, I'm sorry, this is a little bit fuzzy, but 1 month out of the reactor, you can see we have a variety of different isotopes, generally with short half-lives. And so as time goes from 1 month to 100 years to 10,000 years, and finally 100,000 years, at the very long time periods, the dominating elements in terms of radiotoxicity are plutonium. Okay? Not the fission product elements. So this means that plutonium will do a lot in terms of driving my thinking about geologic disposal. It's further complicated by the fact that plutonium has 4 oxidation states that we might anticipate in a disposal environment. This is a plot of redox versus pH. And the only point that you should take from this diagram is if we have these different oxidation states, then the plutonium is more or less mobile. So if we want to evaluate the impact of plutonium in a repository, the repository conditions in terms of oxidizing conditions versus the redox conditions, say the redox conditions and the pH, it matters a lot. And under oxidizing conditions, a little bit of carbonated water, like water in equilibrium with the atmosphere, really holds the plutonium into solution. So the solubility is low, but the mobility is relatively high. Even if the normal thermodynamics of the solution don't hold, plutonium has the property, as do the other actinides, of being able to stick on iron oxides, small, they're called colloids, but very small things held in suspension in water. And so you can see the uranium stuck to these, and plutonium stuck to these iron oxides. This is 10 microns across, so they're very small. And so this is another transport vector. For these reasons, at Yucca Mountain, when you look at calculations of dose to a person 20 kilometers away over time, this is Neptunium, this is uranium, and this is plutonium. You see that the actinides in this particular environment really contribute a lot to dose. However, if we look at the clay deposits, similar type of calculation except for toxicity instead of dose, plutonium, americium, curium, these actinides don't get very far. And so they're labeled as isolated because they decay away before traveling more than just a few meters away from their original site. This is just by way of illustrating that actually the geology counts for a lot. Now, the geology of the repository counts for a lot, but of course the radioactivity is initially in the material that you put that has the plutonium. So that could be the spent fuel, or if we've reprocessed the spent fuel, we might put the plutonium into a very, very durable solid. I'm going to race past a few slides. And so this brings us to the subject of waste forms, durable materials for actinides. And the advantage of having very durable actinides would be then you have near field containment, right? And I'll show you the long-term behavior can be of corrosion and release of a material is probably easier to model than the long-term hydrology and geochemistry of a repository site. There are natural materials that we can use as analogs to verify, misspelled, the extrapolated behavior. Okay? And looking at the time, what I want to do, because I want to leave time for questions, I'll simply point out that actually over the last decades, scientists all over the world have looked at actinide-bearing materials, and so we know a lot about whether we can incorporate actinides into materials. And these are generally selected because they're durable, as evidenced by the fact that many of the heavy minerals, the dark grains you see in a white beach, those are the heavy minerals that survive transport over tens to hundreds of kilometers, and that's evidence of the durability. The difficulty with putting an actinide into a material is this alpha decay. And this recoil nucleus displaces thousands of atoms, let's see, and leaves and destroys the structure, so that every time we have an alpha decay event, we'll have these areas of aperiodicity. It's circled here. Your eyes won't catch it so easily. In these crystalline materials, it's evidenced by the fringes. Okay, this transition from crystalline to amorphous, sometimes called metamict, the important point is it changes the solubility, the release rate, by an order or two, by one or two orders of magnitude. So we can make very durable solids with actinides, with plutonium, but it turns out that nothing's ever as simple as it looks in the first moment. The radiation damage matters quite a lot. And I'm going to jump over a lot and say, so one of the first things our group studied was radiation damage in natural zircons, a mineral very familiar to geoscientists because it's used for age dating, because it contains uranium and thorium, and as a function of dose, displacements per atom, we can measure changes in properties, in this case, a volume change. What's important is we can also dope this structure with plutonium, an isotope plutonium-238 that decays a little faster than plutonium-239, and perform the same experiment. This experiment took 5 years. The natural experiment took 500 million years. Okay? So all I want to say is, one, this is pretty cool, but two, we know a lot about radiation damage accumulation in these materials. And we can see this is the doped with plutonium zircon, beautiful orange when it first is synthesized, but over a few years you can see, due to the expansion, flakes peel off and the color centers begin to dominate the color. Now another material we've looked at is pyrochlor. The beauty here is there are over 500 compositions, but it doesn't occur, at least the compositions we want, in nature. And so what we've done is, instead of the plutonium and doping experiments, we've used ion beams to study the radiation damage. We irradiate the material in a transmission electron microscope. The fringes here mean the material is crystalline. The absence of fringes means that the crystallinity has been lost, and we can follow in great detail, and many now have done this type of work, the accumulation of damage in the material. And we can see in this material that by changing the composition, in this case looking at zirconium versus titanium, when we do an irradiation experiment, if we just take one curve, this is the line. When you cross it, the material becomes amorphous, but at higher temperatures it begins to recrystallize. And so this would be the typical shape of a curve. And as we put more zirconium in the structure, replacing the titanium, the curves move to the left until finally the material can no longer be amorphized. Okay? Now the beauty of using ion beams is now we can investigate a wide variety of compositions. We're not stuck with what nature provides. And in the same structure, before we were looking, I realize I'm going very quickly, we were looking at this atomic site. Now we can look at this one, doing all the rare earths, lutetium, erbium, ytterbium, and so on, and we see that the curves shift over some 600 Kelvin. So the curves are shifting as a function of changing the A and B site cations in this simple structure. This means that we can engineer the radiation response of the material to the amount of plutonium you want to put in it. Many experiments have been done, and so we have surfaces that represent the critical temperatures, that is where the curves bend upwards, as a function of, in this case, the ionic radii of the elements in the structure. So if we put 10% of plutonium in the gadolinium titanate, in 1,000 years it will become amorphous and the release rate of plutonium increases by a factor of 50. If we substitute zirconium, it remains crystalline, even out to many thousands of years. Okay? So we have the possibility to do this type of engineering. And I should point out the gadolinium titanate is very susceptible to radiation damage. Okay. I'll finish in just 3 minutes, so there's time for questions. So what I want you to realize is that in terms of the geochemistry and the hydrology of a site, there's a big difference between tuff and clay. Okay? In terms of developing materials that are durable or not, there's a big difference between the types of materials that might be designed. So with those scientific possibilities, what have we managed to do in the United States? Well, we have a good example of what's happened. And this all goes back to the early 1990s when the former Soviet Union and the United States began signing a series of START agreements and bilateral agreements to reduce the weapons stockpile. And this resulted in each country having about 50 metric tons of plutonium that they're obligated to get rid of, and that's the red horizontal line here. Okay? This is the so-called excess weapons plutonium. And so in the early 90s, the issue of dealing with this excess weapons plutonium really stimulated a lot of the research that I've discussed. So where did we go? Because I'm using this now as kind of a little case study. I've talked about plutonium in the nuclear fuel cycle, but how far do we actually get? Well, the story starts with President Clinton issuing a non-proliferation and export control policy in 1993. The National Academy of Sciences and DOE reviewed options. Excess weapons, plutonium was identified in both countries. And the first part of the story, I want to emphasize that this was really agreements constrained by international concerns from both the United States and Russia. And the United States ended up with what the Russians decided, well, we'll make MOX and get rid of our weapons plutonium that way. We decided to make MOX, but we had some plutonium, which I'll call scrap plutonium, which really would have to be cleaned up a lot to put it in fuel. And so we decided to immobilize that material. And so this was a dual track option. The National Academy of Sciences said, well, if you're going to, whatever you do with the plutonium, it has to be hard to get. So be sure it's at least as inaccessible as the plutonium in spent fuel. And so the dual track option of immobilization meant that, well, let's just take the very radioactive high-level waste and let's mix the plutonium with it to protect it, say, from people who might want to use it with weapons. To shorten the story, or to get to the end, construction on a MOX plant started at Savannah River in 2007. 7 years, and the estimated cost was about $4 billion. Remember, this is for about 37 metric tons of plutonium. Most recently, the plant's over half complete, but the life cycle cost now is estimated to be $30 billion. So that's getting to be pretty expensive for the MOX or the nuclear option. And so now DOE, the administration, has proposed cold standby for the MOX plant at Savannah River. The state of South Carolina has sued the Department of Energy for stopping work on the plant, which Congress authorized, and DOE is reviewing their options. The options are back to actually my old list. Nuclear versus geologic. These are the nuclear options. This is the one that turned out to be so expensive. This is one with fast reactors that would be even more expensive. These are the geologic options, okay? And this is very interesting. The immobilization in a glass or ceramic form mixed with high-level waste, I've discussed that very briefly. A new one is to take the weapons plutonium and just dilute it until it looks like what we call transuranic waste, and send it to a repository in New Mexico called the Waste Isolation Pilot Plant. Number of difficulties. First, when New Mexico agreed to opening the waste isolation plant, spent fuel and high-level waste were specifically excluded. No one imagined you would be taking weapons plutonium and diluting it down, so that's not excluded in the law. But the then Senator Domenici made it very clear in correspondence with Secretary of Energy that you just can't dilute weapons-grade plutonium and send it to the waste isolation pilot plant. Also, the waste isolation pilot plant is based on the possibility of only 6 metric tons. This would send 50 metric tons. So in terms of analyzing the response of a repository, that requires careful attention. And then a new idea, very recent, well, an old idea that's been revived is deep borehole disposal for this weapons plutonium. The working group has issued their first review, and these are the criteria. Meeting the international commitments, the cost, which were so difficult to estimate in the first place, whether we'd be able to complete the mission, technical viability, legal, regulatory, and other issues. And what I want to say is, or the takeaway message, is the other issues are the material science and geochemistry I've been discussing. So 20 years later, we're reviewing essentially the same set of options, but not very well informed by 20 years of progress in material science and geochemistry. And so I'll end by saying we're pretty much in terms of carbon and plutonium where we were 20 years ago. Maybe today with the announcement of the draft regulations for CO2 emissions from coal-powered plants. We can look forward to CO2 emissions decreasing, but we haven't at all been successful in dealing with the plutonium from excess weapons. And I think that is a good signal as to, or a good sign of whether or not we would be successful if we had a full cycle, full nuclear fuel cycle generating much more plutonium. So, thank you very much.
Okay, we have time for some questions, and let's start with students. No students. Okay, all right. Here we've got more students. Okay, all right. How about that gentleman back there?
I'm not a student.
Yeah, sure you are.
Is there any potential for what is called an integral fast reactor of impacting the magnitude of the waste storage?
So this is just an opinion. It seems unlikely to me to have an impact within the time frame of interest, which is in the next few decades. It turns out, and I think this is just life as it is in the nuclear community, that it really is many decades of effort to exploit any very new idea. And if we're looking to have nuclear power have an impact on the carbon cycle, of course the carbon cycle, we're a little bit anxious about that. We have some timelines there. So whatever the nuclear answer is, it also has to be a timely answer.
Okay, all right. How about up here?
So, I have a lot of questions. Don't know, but two anyway. Interesting that you use the block bomb TCS book because it's known to be defective. It didn't even discuss the root cause of Fukushima, which had nothing to do with nuclear power, while the Bureau of Atomic Scientists did, in fact, in one page, explain the root cause of Fukushima. So I suggest that, maybe if you haven't read it, anybody here, read Atomic Accidents by Mahaffey.
Okay, so let me respectfully disagree with you that it doesn't have anything to do with nuclear
No,
power.
I didn't say it doesn't have anything to do with it. I said the root cause is not nuclear power.
Let me respectfully disagree with you in terms of the root cause, because I consider risk assessments as practiced by the nuclear industry as root cause. Okay.
The risk was not assigned by TEPCO and the Japanese government. So the Japanese government failed, yes. But all the other power plants around the region suffered no significant damage, including the TEPCO plant with 4 operating reactors at Fukushima Daini. So there is a root cause that has nothing to do with nuclear power for Fukushima Daiichi, and they do not cover that in the UCS.
So I think there's a wine afterwards.
We do have wine afterwards, so you don't have very long.
There's a lot more things.
Yeah, because, really I think this is a common dodge. Yeah, because we look at one accident and we say, well, look at all the places where there weren't any accidents. Where in fact, I would say the proper risk assessment would have been to look at the entire east coast of Japan, where you have reactors dotting the entire coast. Look at the stress buildup off the coast and calculate the probability that someday some reactor, not a particular reactor, but some reactor will be in trouble. And those probabilities, that approach changes the probabilities quite a lot. And one of the difficulties with the way the nuclear community handles risk assessments is they narrow the question so much that yes, the probability that I'll feel an earthquake today in this spot is pretty low. But the probability over time and over a larger area actually is very high.
So you're saying that the fact that
I think we have to move on, because we have, I think,
you're misleading the audience here.
Okay, we have another question here. Yeah,
But we can continue afterwards.
Yeah, sure we will.
What about the contaminant?
Okay, can we go to you next? I said, yeah,
sorry.
yeah, sorry.
What I feel the solution part is mostly related to the policy issues, how it is to be dealt with. So can't we start the dialogues as the formation of IPCC was there, Intergovernmental Panel on Climate Change. So similar kind of intergovernmental panel for nuclear cycle.
Yeah, actually, that's an excellent idea, and that's already started because there's an international panel on fissile materials that's run out of Princeton. It's on a much smaller scale. I mean, it's a few people and collaborators, but the idea is very similar. You know, let's get as much information together on fissile materials as they're spread around the world and begin to address the problem in a very broad way.
I think it's a high time to go for these kind of things on a larger scale.
Yeah, I agree.
On that encouraging note, I think we're going to wrap up. You will be at the social. We do have a map social, so ask your question there. And anyway, thank you very, very much.